Hello everybody, today I'll be going over an AP Physics C E&M question that I thought was really challenging. It deals with some Unit 8, 9 stuff, conductors and insulators. So I'm going to be going over it. I'm also doing this for myself just so I get some better practice, but I hope this helps you if you had a hard time with this question. Okay, so they gave us this system here with a conducting shell around an insulating sphere and just a little gap here of just white space. And it says relative to the electric potential at infinity, then what is the electric potential at the center of the solid sphere? So it's asking us for the potential from infinity to the center of the sphere. So first, let's begin this problem by writing out what electric potential is. So first we can write that delta V equals VB minus VA. So this means the potential difference is from point B to point A, from final to initial. In the context of the question, we can write this as V sphere, which throughout this problem I'll write as SP, minus infinity. The reason that infinity is our initial is because it says relative to infinity, so that would be our reference point. And our reference point is always the initial position. So that's why it's sphere minus infinity, not infinity minus sphere. I'm saying that because I had that problem. Now that we have this, we can actually use the equation electric potential equals negative integral of electric field. So our bounds, our upper bound would be our final position. So that would be the sphere. That would be 0. And our lower bound, our initial position, would be infinity. You can actually do something with integrals. You can switch the sign and switch the bounds. It's not as positive. It's just a little easier to solve it. Now what we can do with this formula is we can apply it to both of the electric potentials. For the entire sphere system, our bounds would still be infinity to 0, and I'll rewrite it. Okay, so we have that. Now we have to find the potential at infinity. But this would simply just be 0. And the reason is because potential equals the integral of E, right? And E equals KQ over R squared. As distance increases on the denominator here, as this gets really large, the fraction becomes smaller, right? So that means it's approaching 0. So as this approaches infinity, we can just say that it's 0. So now we have an equation that leads us to our answer. But there's a problem. E is not the same all around for the sphere. The electric field is different here, it's different here, it's different here, it's different here. Conducting materials and insulating materials have different properties when it comes to charge distribution. And because they have different properties in charge distribution, that influences the electric field. We're going to have different values of E from 0 to A, from A to B, from B to C, and from C to infinity. Okay, so now that we know that the electric field is different at different points, and this is our expression, you can split the integral using the additive property. We're going to split it up like so. Okay, so now I've just split up the integral into 4 different parts. And I know this already looks really horrible. This got split up into 4 different parts for the 4 different integrals. So if you look at it, it's actually not too bad. It goes from A to 0, B to A, C to B, and then infinity to C. And we can go back to our little model we're given here. We have to account for the electric field from A to 0, from B to A, from C to B, and then from whatever's outside, infinity to C. It just says that the total potential is going to be all the integrals of electric field added together. So for that, we have to split it up. Okay, so now we have to integrate all these separately. So let's start with the one from A to 0. So that'd be right here in this little poorly drawn sphere model I have here. So let's start out. So we know that this is a uniformly charged insulating sphere. So that means E equals KQ over R squared, right? But the problem is, when we put this into the integral, all this is a constant, because in this case, R squared would be A squared. So this is all a constant, and we can't integrate a constant. So what we have to do is we have to bring back R. So how are we going to do that? We just have to do a little bit of algebra. So what we're going to do is we're actually going to put the R here and make it A cubed. Yeah, this one was a little tricky for me. I couldn't quite get there. But Just know that this might pop up on another MCQ, FRQ. You do this when you have an insulating sphere and you need to reintroduce R into the equation in order to integrate it. Now the reason this makes sense is if your R is A, then it cancels out one of the A's, and so it'd just be KQ over A squared again. And that makes sense because E is KQ over R squared. So sorry if my explanation was a little rough on that one. But okay, so now that we have this expression, we can now go ahead and integrate it. We can take out the constants. This would become R squared over 2. And then this would just end up becoming KQ over 2A. Okay, so this is your expression for the first of the 4 integrals. We're just going to write this as V sphere minus VA because the final position is from point A and it goes to the sphere. Okay, so this is our first of the 4 integrals. Okay, so for our second integral from B to A, again in this poorly drawn model, it's going to be from inner part of the shell and the edge of the little sphere in the middle. Okay, so what's going to happen for this one is that the solid sphere we just solved the electric potential for, it's going to act as a point charge. And this is because the charge was evenly distributed because the question said it was a uniformly charged insulating sphere. So it's just going to be like a point charge that's generating the field. So what's going to happen is we can just solve it normally. KQ, BA, 1 over R. Okay, so that's just going to be minus 1 over B. Okay, so the next electric potential that we have to solve for is from C to B. So, and again, another poorly drawn model. It's going to be the inside of the conducting shell. But the thing here is that a conducting shell, like this one, doesn't have any net charge. And this is because in conducting objects, all the charges spread out uniformly. So therefore, there is no net charge. And since E equals KQ over R squared, if Q is 0, then E is 0. And the integral of 0 would just be 0, I think. So yeah, it's just 0. I'll write that in the purple font, or purple color. Okay, so for this last integral, this would cover from infinity to the outermost shell. So in order to do this, first, we must consider what would be our value of Q. In all the past problems, we've had to deal with Q and E equals KQ over R squared. But what would be the Q this time? And the answer to that is actually just the solid sphere again. So similar to the second integral we did, the solid sphere in the middle is going to act as a point charge. And the reason we can do this for this last integral here is because the conducting shell from the third integral here, it has no net charge. And that means it does not influence the electric field. For that reason, we can just use the Q of the solid sphere again. It's going to act as another point charge. That means, just like the second integral we did, we can just integrate normally. So that would give us, let's see, KQ over R. This goes away. That would give us 1 over, so this would be KQ times this. This would be 0 because the denominator is infinity, and as the denominator of any fraction approaches infinity, it would be 0. And that would give us KQ over C. Okay, so the heavy lifting is done now. Now all we have to do is just combine all the integrals back together, smash them up, because what we did initially is we split up the integrals and now we just put them back together. Okay, I'm going to use a bright color yellow for this just so it's painful to see. Okay, so the first potential we got is KQ over 2A. The second integral is KQ 1 over A minus 1 over B. That can just become KQ over A minus KQ over B. The third integral, which is 0. The fourth integral was KQ over C. And now it's just algebra. So you can take the KQ out of the equation and simplify the denominators for A. And we get KQ times 3 over 2A minus 1 over B plus 1 over C. And then the 3 over 2 here is simplified in the College Board answer to 1.5 for some unknown reason, decimal and a fraction, I guess. And going back to the College Board, here's the full explanation if you'd like the College Board explanation better. Okay, so here's a quick overview of everything we did. So first, we defined what electric potential was. We were using infinity as our initial point we call 0 in the middle of the solid sphere as our final point. So we used the equation from the equation sheet, V equals the negative integral of E. We used a calculus tool and we turned it positive, and then we turned it into this equation. V equals the positive integral from infinity to 0 of electric field. V is our answer, of course. We had to split up this whole thing into 4 different parts using the additive property of integrals. And the reason is because the electric field was different from 0 to A, from A to B, from B to C, and from C to infinity. And the reason it was different was because of the charges. The charges were distributed differently. E was not one single value that we could integrate. All we did was solve for each of the integrals independently, found each of the independent potentials, and then we just added them back together. Then it's just algebra. You just put it back together. Conductors and insulators were a challenging topic for me. We're doing circuits right now, so probably more videos on those. But if you have any questions or comments, please leave them down below. And thank you for watching.